Hello, my name is Matt Nowell. I'm the EBSD Product Manager here at EDAX, and I'd like to welcome you to our on-demand webinar entitled Characterization of Lightweight Structural Materials for Automotive Applications using EBSD. Before we get started, I'd like to cover a couple of housekeeping items. First, at the bottom of your console, there are a couple of different widgets you can use. The first is the Q&A widget. You can use this to submit your question. Obviously, for an on-demand webinar, these will be submitted via email and be answered via email after you submit them. The other widget of interest is the resource list. It looks like a green folder at the bottom of your screen. From this, you're able to access a copy of the presentation if you're interested. With that, I'd like to get started with the presentation. So what I'd like to do is outline what I'm going to speak about today is first, why lightweighting is important for automobiles and transportation. Then I'm going to introduce EBSD and OIM and tell you what it is. And then I'm going to try to show you what we can do with OIM. And I'm going to show you some examples from alloys of steel, aluminum, and magnesium, and then try to give an idea of how OIM can help improve the lightweighting efforts for automotive applications. So, the first question really I asked as I started getting into this is why lightweight materials are important for automotive applications. I'm recording this in early 2016, where right now gas prices are actually pretty low, so you don't think quite as much about fuel efficiency when that's the true case. But over, the last few years to many decades, really, there's been a push to improve the fuel efficiency of automobiles, and so there are actually legislative mandates in different regions here. So I've put here the U.S. average fleet efficiency target of about 55 miles per gallon by 2025, a target of 57 miles per gallon in the EU by 2020, and a Chinese target of 47 miles per gallon for 2020 as well. And so, there's certainly a number of geopolitical factors pushing the automotive industry to improve fuel efficiency, and that can be cost of fuel, it could be global warming, climate change. All those things are driving forces to say it's important to improve the fuel efficiency of a vehicle. And one of the most targeted ways of doing this is reducing the weight of an automobile. So I put here a 10% reduction in weight can improve fuel economy by 5 to 8%. If we look at the chart on the bottom right there, that shows a number of different possible pathways of improving fuel efficiency. Weight reduction really is identified as one of the key approaches that will allow the automotive industry to achieve these aggressive efficiency goals. So when I talk about lightweight materials of interest for EBSD, EBSD is a technique that looks at crystallographic crystalline materials. And so I'm going to talk about lightweight alloys. And so this chart here gives an idea of what's the strength to density ratio of different materials. The ones targeted for the automotive application are different steel alloys, aluminum alloys, and magnesium alloys. All with different applications within the automotive frame. Other materials there identified are glass and carbon fiber. Those we don't really target with EBSD. I'm going to be talking about the metallic alloys. And so when we talk about these materials, what's important is the entire life cycle cost. And so, the material, the manufacturing needed to integrate it into the car body, the life cycle of the material, can you recycle it later, can you reuse it, are all factored in to try to understand, is it cost efficient to use these materials in an automotive application. It's easy enough from a materials point of view to select a material, but in the end, the consumer wants to buy a car at a certain price point, and they have to bring those two together. And so as part of this, not only do we have to select a material, we have to be able to fabricate it into a useful shape, form it into a useful shape, and then we have to put them all together. And so all this has to be done in sort of an integrated fashion to successfully, introduce and integrate the materials into an automotive design. So this just shows a little schematic. The BIW is body in white, is sort of the structural frame of a car. And it shows where different materials can be integrated together. So it shows some different aluminum produced by sheet and die casting and extrusions, some different steels, some magnesium that are all brought together in a way to sort of minimize the weight but meet all of their requirements, both from a weight and from a performance and safety perspective. And so looking into this, a lot of times as different companies are moving forward along this roadmap to lightweighting, there are different stages of lightweight material implementation that are planned and expected. As the materials are introduced, the technology and the expertise to use these materials are developed and going forward. So this is just a little example from a Toyota concept, is that, you sort of have a baseline vehicle here. There's a high development car, which is, this one's going to introduce more advanced materials and go to a lower weight, but it's going to take more, research and learning and development to be able to do that. But there's also a lower development sort of stepping stone where more available materials and processing is currently available, so you can sort of step your way along to using these materials. And then when we talk about it, each little component of the car, they all have their different specific requirements, different requirements in terms of weight, processing, and also material properties. And so this was just a neat example that I saw of, this is for what's called a fuel tank guard. And they came up with an idea of creating this with a hot stamp processing route. And you can kind of break this up into a mechanical processing, a thermal processing, and then what's happening with the microstructure during this processing to get an idea that, as they do this hot stamping, they're taking the material, they heat it up, they press it, and then it cools back down sort of in the shape you want. And as you do that, the steel microstructure develops through that thermomechanical processing procedure. And it's that final microstructure that actually will give you your material properties. And in this case, this example, through developing this procedure, came up with a material that was 7% lighter, 40% fewer parts, and almost 90% less welding than sort of the baseline part that was used previously. But as they do this, you need to make sure your final result has the right microstructure. And so what we need to be able to do is to be able to measure that microstructure to help correlate that with any process development. So the approach that I'm going to talk to you today about is what we call OIM, or Orientation Imaging Microscopy, which really falls into that classical material science idea of your materials processing will define your microstructure defines your properties, and so as you adjust your processing to get different properties, you're essentially altering the microstructure. And so by being able to better characterize the microstructure, you get a better understanding of the relationship between the processing and the final properties via the microstructural constituent measurements. And so as you push to minimize weight and optimize properties, you want to know if I go to a higher temperature, if I cool at a faster rate, what is that actually doing? Because then you can come to more of a fundamental understanding of saying, if I want this property, I really want this microstructure, how do I get it? And OIM and EBSD really ties into the crystallographic aspect of materials. Most materials are generally anisotropic, and by that I mean they vary with orientation. And so the easy way to understand this is to think of breaking a piece of wood. Shown on the left, if I want to look good when I'm doing my karate moves, I align the wood block so it's in a weak orientation. The grains are aligned with the direction of force. If I want to, play tricks on my kid, I arrange it the other way so that the force is perpendicular to the long grains there, so it's in a stronger orientation. And the same force will introduce different amounts of damage. That same concept can apply on a crystallographic scale, where some orientations will be stronger, some orientations will be weaker, and different properties will vary in different directions. Now, often when you first start learning about this, it's assumed that you get enough grains together, they point in enough different directions, and the anisotropy is averaged out and it becomes isotropic. This isn't really not necessarily always true. Most forming and fabrication processes will introduce some amount of anisotropy into your final material. And so being able to measure this is important. And so, you can use stuff like neutron diffraction to measure a volume or X-ray to measure an area. But with EBSD and electron diffraction, we can go to very point-specific sampling. And what I'm going to try to do is show some advantages of this approach. So the way to think about OIM, or orientation imaging microscopy, is automated EBSD or automated EBSD mapping. And so EBSD is an SEM-based characterization technique. So you can see here on that little schematic in the top left, we take our sample, we tilt it to about 70 degrees, we fire the electron beam onto the sample, the electrons interact with the sample, interact with the crystal lattice, they diffract within an individual grain, that diffraction comes back out, it's backscattered, and we detect that with our EBSD detector there. And so the reason we tilt the sample so the electrons go towards the detector efficiently. And then with automated EBSD, what we do is we define a measurement grid, as we're shown on the top right there, and we just define an area and a step size to measure from. And so at each point, we kind of go through the flow shown on the bottom there as we get a diffraction pattern. We process it there in those middle two steps of finding the position of the diffraction bands via some image processing algorithms. And those bands correspond to different crystallographic planes. So by knowing the spatial distribution of those planes, we can calculate what's the crystal orientation and what's the crystal phase present at each point. Once we have that, then we can start to visualize the microstructure by coloring different points via different metrics, be it orientation or be it by phase. And I want to try to show some examples of that. So the first example I want to show is for what's termed a twip steel, or a twinning-induced plasticity steel, that are a class of alloys that have been engineered to enhance the ductility to help absorb energy in an automotive application in the event of a crash. So if we look here at the chart on the top right there, it gives an idea of the property curve relative to traditional steel alloys, that the twip steel is an area where it has higher strength and higher ductility relative to other alloy classes. And so this occurs through the formation of deformation twins that as a material is strained, it causes these twins, it increases grain boundary density, and it blocks further dislocation movement. So the question is, how can EBSD help understand twin steel development and performance? So what I'm going to start with is this little evolving chart, and I've just titled it "What We Can Do with EBSD." And on the left there, we're going to put, what type of analysis can we do, and what tools do we have for interpreting the data. So the first thing I've put here is diffraction-based defect imaging, and then put mapping as a visualization type of a tool. So the first measurement I want to talk about is what we call EBSD image quality, or IQ. And this is just a value that measures the sharpness and intensity of the diffraction bands in the EBSD pattern. And then what we're able to do, you can see in the example here, in a recrystallized part of the material where the crystallographic lattice is very pristine, we get nice sharp diffraction points. If the material is deformed, the lattice is a little curved, the diffraction becomes a little bit more diffuse and not as sharp, not as bright. And so that would cause a lower image quality value. So what we can do is we can measure an area and then map out this image quality values, where the lowest points are the darkest, the brightest points correspond to the highest image quality values, and get an idea of I've called this a defect-based type of an image, kind of similar to dark field imaging. So if we look at a trip steel example with the IQ map, we see that the contrast in that map shows quite a few different microstructural features. We see grain boundaries, we see twin boundaries. We can also see little pieces of dust where the pattern is not shown completely and it turns out a little bit darker. We see linear features. We see contrast changes within the grains. So the next question to ask is to say, what can we learn about these different features using EBSD? So the next thing here is based on just imaging, we can go to measuring the crystal orientation. And as far as a tool, we also have the ability of doing point and click type of an analysis. So to show an example of this here, what we do is we go into specific grains, click different areas, and display the local crystal orientation by showing a little unit cell that you see on the microstructure. It's important to note that EBSD is measuring the complete three-dimensional orientation of each point, so that's why we can show the little unit cell. And we term this type of point-and-click analysis interactive analysis, and we have a full interactive toolbar for this sort of an approach. Alternatively, we can go a little bit further and we can color each pixel according to the crystallographic orientation. So in this case here, you can see there's a little stereographic triangle there that's colored. So red points would be an 001 orientation, blue would be a 111, and the green would be a 101 orientation. The steel alloy is a cubic alloy, and that's why this stereographic triangle is used. In this case, we're shading the colors relative to the surface normal direction of the sample. And so what we see is there's a few different grains there, but we also see within the grains some variation of color within the grains. And that's saying that within a grain, the orientation is changing from the deformation in the material. And what we can see here is we can compare the image quality map to the color map, and I can go into where we see changes in that image quality. We can see there in that center grain that image quality variation. If I click across there, I can see how the orientation is changing across that grain, causing both the image quality and the orientation contrast. So the question to ask here is, can we quantify these shifts? And with those shifts, the idea is shifting from a crystal orientation measurement to a crystal misorientation measurement. And so with that approach, I'm going to look at what we'll call a line analysis. And with a line analysis, what we can do is go in and define a line in the microstructure. So I've gone and drawn that in as the grain as shown there. And we're going to show two different distributions. We can draw what we call a point-to-point misorientation, which shows as we go along that line from one point to the other what misorientation is present. You can see that's the red distribution there. And in general, that's very low. There's small misorientations occurring within the grain. But if we look at the point-to-origin distribution, which is the blue line there, you'll see that those small misorientations are cumulatively building up into large rotations. So we can see how that total grain deforms spatially while still measuring small misorientations on a point-to-point nature. So once we're measuring those small misorientations within a grain, we can start to think about quantifying plastic strain measurement. So plastic strain is what happens when we permanently deform a material past the elastic limit. And so we start to introduce dislocations that cause small lattice changes of misorientation. So we can measure that with EBSD, and we can do it with a point, kernel, or grain-based analysis. So these are maps where we're trying to show the distribution of plastic strain. And so here are two different approaches. The first is what's called a local orientation spread map, which is shown on the left. This looks at the misorientation in a local kernel of points. These are on a scale here where blue would be less plastic strain. As the colors go from blue into the yellows and greens and then to the reds, we see that where there's more strain present. So we can see that strain is localized in certain grains and near certain grain boundaries. We can also compare that to what we call our grain reference orientation deviation, or GROD map. In this map, we calculate the average orientation of a grain, and then with every pixel within a grain, we calculate the misorientation between that pixel and the average, and we plot that on the color scale. And you can see in that case, the color scale goes clear up to 33 degrees. So there's a point within the grain is 33 degrees away from the average orientation of that. So there can be quite a bit of bending present in some of these grains, but we can visualize where this plastic deformation occurs. We can see where it is relative to different grain boundaries or triple junctions within the microstructure. And that leads to the idea of grain boundary analysis. Not every grain boundary has the same type of influence on material properties. And so we're able to kind of look and see what type of boundaries occur in a material. So we show this. This is kind of a basic way of looking at it. This is looking at one of these lined, striped areas within a grain. And if we look at the misorientation that evolves there, we see there are lots of peaks near 60 degrees, and then it comes back down. So that 60 degrees is sort of a magic number. And if we look at the distribution, rather than looking at a line, we look at the misorientation distribution for all the points. Greater than 5 degrees in this case, I'm going to filter out those low-angle misorientations from plastic deformation. But we're going to look at the point-to-point correlated distribution. We see that on the left. We also see it on the right as the distribution in red. We also look at the uncorrelated distribution, and then we also show a random distribution. And what we see is that relative to the random distribution, there are certain peaks that are occurring in the correlated and uncorrelated distribution, which give us an idea that specific grain boundaries are developing within the microstructure. And again, one of those peaks is near that 60 degrees. So one of the things we're able to do is go into what we call interactive highlighting. So for interactive highlighting, I can take our distribution, and in this case, I've just dragged and dropped my cursor across the whole distribution and assigned a color scale to this. And I can adjust the color scale, and I can adjust where I drag my colors. But basically, you see for the low-angle boundaries here, we start the blues, go into the greens, the yellows, the oranges, and into the reds. And what we see is there's a lot of red boundaries now in that microstructure, and those red boundaries correspond to those striped boundaries within the grain. And so that leads to the idea of, those striped parallel boundaries, of course, make us think of twin boundaries. So we can actually do some twin boundary analysis with EBSD and OIM. So twins are boundaries with very specific misorientation geometrical relationships that can be described in what's called CSL, or coincident site lattice theory. And so primary twin boundaries are what are termed sigma-3 CSL boundaries. If you take a grain and you twin it, you'll get that CSL3 relationship. If you twin it again, you'll get 3 to the n, or in this case, 3 squared, or sigma-9 second-order twin. And so what we're able to do is to classify all the boundaries in there, is to say, are they low-angle boundaries, in this case 2 to 15 degrees, are they high-angle boundaries greater than 15, or are they CSL boundaries? And so then these are twin boundaries. We can see that there's a pretty high fraction of CSL boundaries present in the material. It makes sense. It's a twip steel with lots of twins. We'd expect lots of CSL boundaries. We can also classify those as different types of CSL. So we see there are primarily sigma-3 boundaries, but there are a few second-order sigma-9 boundaries in the distribution as well. The next thing we can do is we can talk about grain size measurements. We can combine that with the idea of measuring grain sizes with and without twins and twin removal from grains. So to measure the grain size, what we need to do is we need to group together pixels of the same orientation. So to calculate grains, we need to group together points that have the same orientation. But to do that, we have to define some sort of a grain tolerance angle to decide when one grain changes from one to another. So in this case, I've used 5 degrees as our grain tolerance angle. So we go pixel by pixel in the measurements and say if the misorientation between those 2 pixels is less than 5 degrees, it's going to be within the same grain. And if it's greater than 5 degrees, then it's going to be a different grain. And so as we repeat that process for the whole measurement grid on the left, we determine the grains, and then we just randomly color these to show the size and morphology of the structure. So you can see, we see the grain structure, and we see a number of the fine lamella twins in a number of the grains. But as we go through this grain grouping approach, the other thing we can do is to say if the misorientation matches a specific relationship, so in this case a twin relationship, which would be a 60-degree rotation about a 1-1-1 crystallographic axis for the primary sigma-3 twin, we'll say let's take that specific type of boundary and ignore it when we're calculating our grains. And when we do that, we get a different grain structure shown on the right where we see our grains where we've excluded the twins, and we see our effective grain size is much larger than if we include the twins. And so one of the nice things about EBSD is we can actually calculate the grain size distributions from either a twin included or a twin excluded defined grain structure. And that's just important because for certain material properties, your twins can have a very different effect on properties than, say, a random high-angle boundary. And so being able to calculate grain sizes from one to the other is important. And so this shows, and of course, if we go to a lower magnification and we take more measurements or even a larger area with a coarser step size, we can collect more grains to get a better idea of counting statistics. So this is just an example, where we can collect more than 10,000 different grains to get a good statistical distribution of the grain size and shape to sort of quantify a microstructure. So we can kind of conclude this little section by saying, how does EBSD help us with twip steel? Well, EBSD can be used to measure the twin boundary fractions, the local deformation, and the grain size, which can help us understand the microstructural influence has on improving the strength and ductility of the materials. So at this case, I just wanted to take a quick moment to talk about grain size. And this is just a great quote from an article in Materials Today a few years ago, where it says, it's well known that grain size is the major microstructural parameter in dictating the properties of a polycrystalline material. And so, these are just 2 different equations. The one on the left is your Hall-Petch relationship, which gives an idea of how the yield stress is influenced by the average grain size. The one on the right gives an idea of the steady-state strain rate, where grain size is a parameter. And so by knowing the grain size, we can correlate that to a lot of different material properties. And so EBSD is a nice tool for measuring that. I mentioned earlier that we define a grain tolerance angle, and EBSD is a great tool for looking at grains under different grain tolerance angles. There's a great question of saying what's the what number defines a grain. I don't know if there's a great answer, but EBSD and OM is a great tool for looking at that. And this is just a really nice example. The image on the top left there shows an image quality map, where to me it reminds me of a lot of a TEM type image where we see a lot of grain boundary contrast in the material. The image on the bottom left shows an orientation map. So here the colors are showing orientations. We see that this material seems to have a lot of, I'd almost call it like a subcell type structure. When we create the grains, we randomly color the grains. If we do a grain tolerance angle of 10 degrees, shown in the middle left there, you'll see that measurement area is really broken up into 3 primary blocks of grains, a top, a middle, and a bottom. If we define the grains at 1 degree, we see that top block still is about the same, even though there's lots of grain contrast or boundary contrast we see in the image quality map. But the middle and bottom grains start to section down into little subgrain, subcell type structure. And if we go down as low as a half a degree, now that top grain breaks into different structures. So, a lot of times measuring a grain size will depend on how that grain boundary is influencing the property of interest for maybe which of these would be appropriate for trying to model in an equation. And this is just an example here. One of the things research is focused on is working on using different methods of introducing superplastic deformation to refine and control the grain size. So this is what's called equal channel angular pressing or extrusion, where basically you push a material through a die that takes a strong turn. In this case, it's 90 degrees. And so your press sample comes out with the same cross-sectional area, but the microstructure can be significantly influenced and varied depending on the number of passes and the route. So you can push it through and then turn it 90 degrees and push it through again. And there's different routes that go through that way. So you can see this is an example from aluminum from that same Materials Today article. The uncompressed structure shown on the top middle there, very large traditional grains. When it goes through different passes here, we see very different microstructures that evolve. And EBSD is a great tool for sort of showing those as a functioning of processing route. So that was aluminum. So superplastic deformation is one way of influencing aluminum properties. Aluminum is used in a wide range of different applications, your powertrain, your chassis, your body in white, also your engine components. Aluminum has formability that's necessary to produce some of the complex shapes economically, but it's important to note the crystallographic texture of aluminum and aluminum sheet will strongly influence this formability. And then being able to join aluminum components is also an important aspect in terms of the total manufacturing process. So this little chart just kind of shows the miles per gallon improvement by introducing different materials. So we can see there that aluminum sheet can get pretty significant improvements in miles per gallon at a relatively efficient price point. So when we start to do EBSD with this, again, just building along this chart, one of the first things I wanted to show is large area analysis. So this is just an example from an aluminum friction stir weld. And so this is a solid-state joining technique that reduces the time and energy necessary to join aluminum together. And so in this case, this is EBSD data collected from a 27 millimeter by 7 millimeter area with a 10 micron step size spatial resolution to image the texture and the orientation and the microstructure of this friction stir weld. So you can see the base material on the left and right-hand side, and then we see the weld nugget there in the middle. Kind of has this onion ring type of a pattern of different layers of grains. But we can get a large area view of the microstructure. And so I highlighted friction stir weld. Honda used friction stir welding for welding of dissimilar metals in the 2013 Accord. And so that was important because that's sort of a mass-produced automobile. These welds are as strong or stronger than conventional MIG welds. Results in 25% body weight reduction and 50% less energy. So it's very appealing from a total perspective. And so, friction stir welding, it was developed a lot in the aerospace applications, but finding applications in the automotive world. This is just an example. I put a quote-unquote modern, at least a more developed friction stir weld to show the orientation map there on the left. So the base metal transitions much more quickly into the heat-affected zone of the material. We also can use that local orientation spread map to see the amount of deformation present at the weld interface in the weld. And of course, from these large area maps, we can also go to the idea of data cropping and merging to be able to play with these larger data sets. So this is just an example going into taking that large friction stir weld area and defining different areas to create a subset using a cropping function. So we can crop out a single area or multiple area, and then we can add these to the project for easy analysis in comparison to the large area. So this is just an extraction right at the heat affected zone here. And so we have on the left the base material and sort of the grains that are bending into the weld. The right there shows the grain map, so we can see there's some long grains there, and then some smaller, more equiax grains in the structure. And so the question is, how can we analyze this particular area of the weld a little bit more in detail? So that leads to the idea of what we call data partitioning, or taking a subset of the total data set and performing analysis just on that subset to sort of glean information from a specific component of the microstructure. So here what we've done is we've drawn a grain size distribution on the left, and then applied interactively a color code across that grain size distribution. So the small grains are blue, and then they go into the yellows and then up to the reds as the grain size get larger. And we can apply that color scale to the map to see the spatial distribution of the grain sizes on the image on the right. So we see the small blue grains, the large sort of non-equiax, more of a elongated red grains bending from the top left down towards the bottom right. So here now what I've done is I can go into the software and adjust my color scale. And rather than going across a complete color spectrum, I've just gone blue to red to make sort of a two-phase or two-categorical distinction between grain sizes. So in here I've just said if it's less than 50 microns, I'm going to shade them blue. If it's greater than 50 microns, I'm going to shade them red, and apply that color scale. So here I've sort of differentiated by a 50 micron selection. And then we can create a subset by either side. So I'm showing here the orientations of the smaller grains on the left, the orientations of the larger grains on the right. And in addition to the orientations, now I fit our shape ellipses to get an idea of the grain shape. So obviously the smaller grains are much more equiaxed. The larger grains have a lot more of that needle shape aspect ratio and alignment than the smaller grains do. One advantage of EBSD is we get spatially specific data. If we compare measurements with XRD, which will measure some of the same information from an area, what we lose is that spatially specific data, and we gain that with EBSD. And the reason that's important is that the spatial distribution of these measurements can influence performance. So this is just an idea. This are two sections from different areas of an aluminum extrusion. So we look at the orientation map there on the left from the center, and then from the edge of the extrusion on the right, you can see they have two strong extrusion components. There's a blue 100 component and a red, blue 111 and a red 100 component. We look at on the right, it has a similar red-blue distribution. The area fractions of both are actually pretty similar as well, but we can see the spatial distribution is quite different. There are much larger clusters of a given orientation towards the center than there are towards the edge. And so if you were to measure this total, this area with XRD, you wouldn't be able to tell there's a difference between these. And if you look at, grain size and texture on this, you don't see a difference. It's only by seeing the spatial distributions that these become more obvious. So this is just a quick summary for aluminum. How does it help us with aluminum for characterization is we can measure the orientation, grain size, and shape within different regions of a friction stir weld. That would allow us to adjust the welding parameters to produce an optimized microstructure with the properties you want from the weld. So the third material alloy I want to talk about is magnesium. Magnesium is attractive because it's both lighter. It's lighter than aluminum and steel, so it's desirable. It has the mechanical properties you want. But magnesium is hexagonal close packed. It's a hexagonal crystal structure, which is inherently more anisotropic than aluminum or steel, which are both cubic. And with that, aluminum will have fewer slip systems available, which affects the formability. And so being able to understand and control the anisotropy is really a key factor for being able to implement and integrate magnesium into an automotive application. So one of the things we can talk about is texture analysis or preferred orientation analysis. Just as a quick review, I'm going to show what we call a pole figure. So a pole figure shows the distribution of a given crystallographic plane relative to a physical sample surface. So in this case, we often talk about the normal direction of a sample, and that's just sort of the direction coming out of the sample surface. But we can also have in our measurement frame an RD, a reference or rolling direction, or a transverse direction with is orthogonal to that. So if you imagine your right-hand rule sort of thing is your normal is often your thumb, your RD is often your index finger pointing down the direction of tilt, and your transverse direction is 90 degrees to both of those. And so when we show a pole figure, we look at the distribution of a specific crystallographic pole. In this little schematic, we're showing it to the 100 faces of a cube. We put the cube in the center of our measurement reference frame. We show where those poles are on the surface of a sphere there, but then we take that three-dimensional sphere, we convert it to a two-dimensional projection to show that as a pole figure. So we see where those poles are located in sample space. We can see where those three poles are, and we can look at the top hemisphere, the bottom hemisphere. But with magnesium, we're going to generally look at the 001 or the basal pole distribution. So if we look at that here, this just shows a little schematic. So we're interested in the 001 pole. So if we have it in that frame, the pole will be pointing straight out. There are other planes that would be possible, but we'll focus on that basal projection. So this is an example from a piece of wrought magnesium alloy. It generally has this strong basal texture, and we can see that sure enough we do see a strong basal texture, but it's sort of skewed. It has sort of an upside-down comma-shaped distribution to it. So the question is, can we learn anything from that sort of asymmetrical distribution of the pole? So what we can do is we can interactively analyze this pole figure, and I'm just going to go and click on the center of the distribution, and I'm going to specify a 20-degree angular tolerance range from that, and apply the color scale, the blue to red color scale, sort of the default, and then show that on top of an image quality map on the right, and we can see that the center of that distribution corresponds to the top 75%. Of the measurement. So something happens spatially where at the bottom this skews a little bit. So now what I've done is I've selected a single color for both, and I've clicked on a point to show a red distribution and then a blue distribution. So we see a strong texture that's developed, and then it's shifted into a little bit different area in terms of this part of the wrought alloy component. And so clearly we have an inhomogeneous microstructural distribution that we've identified by analyzing the asymmetry of that pole figure. And so just as a quick note that, EBSD can measure this preferred orientation, it can measure the texture. Texture strongly influences the formability of magnesium. And then control of this texture allows you to improve your properties and forming processes. And that's just a little schematic showing where magnesium can be integrated into different components. So that's sort of a summary of what how EBSD and OIM can be used in different ways to show different ways we can measure microstructure on these sort of lightweight structural materials for automotive applications. I put here looking forward. This is just a really nice quote from an Actimet paper from a couple years back. where it says crystallographic texture engineering through a combination of intelligent processing and alloying is a powerful and effective tool to obtain superior aluminum and magnesium alloys with optimized strength and ductility for automotive applications. This was an article in a special issue that was titled Material Challenges in Tomorrow's World. And I think the important part is if you're going to try to push the improvement of optimized strength and optimized ductility for these applications through texture engineering, EBSD is really the ideal tool for measuring the texture. And so, you can't really engineer texture if you don't measure it. And so EBSD is a key for being able to optimize these alloys for these applications. And again, that applies to magnesium because it's hexagonal, close-packed, limited number of slip systems available at room temperature. The more the accommodating the deformation through twinning or dislocation makes magnesium susceptible to orientation effects and therefore susceptible due to texture effects. And so to improve formability, we want to get away from these basal textures we showed from that example. And so, what we want to do is we want to be able to use EBSD to measure the homogeneity, the phase distribution, the grain size, and the texture, as well as whatever plastic deformation and twinning occurs. So texture engineering will aim to improve formability by getting favorable alignment of the basal planes with the deformation direction. And then by refining the grain size, we can activate additional deformation mechanisms such as grain boundary sliding, which improves formability. So this is just a slide kind of showing some of the approaches being used to improve magnesium. So alloying with different materials will activate different slip systems. Introducing twins prior to room temperature deformation improves formability, and to very different rolling routes to improve the texture, strength, and formability. And so for all of these, being able to characterize the microstructure with EBSD gives an idea of what's occurring fundamentally within the microstructure to give these properties. And then just to summarize for aluminum, aluminum is face-centered cubic, has multiple slip systems, is a little bit easier to deform. But you can get prominent texture changes in aluminum due to strong selective recrystallization. So as you deform material and heat it up, certain orientations will then recrystallize and grow. This rolling and recrystallization textures will affect your sheet formability and forming limits. And then alloying aluminums will play a major role in inhibiting grain boundary mobility and controlling grain size when heat treating your materials. So to wrap it up in summary, EBSD is a powerful microstructural characterization tool that will give us information about crystal orientation, grain size and shape, grain boundary character, twinning character, crystallographic texture, preferred orientation, and phase distribution, as well as plastic deformation. This information is useful for helping to develop materials and processing routes and forming routes that allow us to implement different lightweight materials into automotive and aerospace applications. And then once we've integrated these lightweight materials, the cost efficiency and fuel efficiency of the final vehicles will improve and meet the requirements of the automotive industry. So with that, I'd like to thank you for your time for listening to this webinar and invite you to submit a question via the Q&A widget at the bottom of the screen, and we will reply via email when we get that. Thank you very much.